Okay, so let's continue the discussion. So this specification of the PDF is critical in determining a good parameter. In an actual problem, we are not given a PDF, but must choose one that is not only consistent with the problem, constraints, and any prior knowledge, but one that is also mathematically tractable. So this is a challenge. This is a challenge. So the question is, why do we know that this density is a Gaussian? That's the problem of specification of the PDF. So it's a difficult thing. It's a difficult thing because in an actual problem, we are not given a PDF, but choose one that is consistent and also mathematically tractable. So as an example, we consider the Dow Jones Industrial Average. Uh, so if we try to look at that, uh, this is hypothetical Dow Jones average. So it's going upwards with with the uh, the time with the time. So uh, we're going to determine how the Dow Jones average. It's an index. The index. It's a numerical index. Goes with the time. So that's uh, the the problem we are trying to see. Okay, so it might be conjectured that this data, although appearing to fluctuate, actually is on average increasing. So to determine if this is true, we will assume that the data consists of straight line embedded in noise. So the problem of choosing a model, mathematical model, as we see in either this Gaussian or this mathematical uh, straight line, straight line embedded in random noise. It's always a choice. It's not. It's not like we have a absolute truth about this because uh, to know a physical system to the degree of assuming an absolute truth uh, is not practical. So it's not practical. So we always have to assume some kind of model, and we know that the model may or may not be 100% truth, but it's accurate enough that we can use it in an engineering applications. It's true or truthful enough for us to use that in our engineering applications. That's the sense we are trying to see, rather than assuming an absolute truth. Okay, so uh, that x is a plus bn. That's a straight line, right? X. Let's go again. Let's go again. This index is a straight line plus some kind of noise. Okay, so that is this thing. It's xn equal to a plus bn plus wn, and this is the noise. A reasonable model for the noise is that wn is white Gaussian noise. It's white Gaussian noise, which we often refer to as WGN, or each sample of WN has the PDF N0 sigma square, and that denotes the Gaussian distribution with the mean 0 and a variance sigma square. And it's uncorrelated. with all other samples. Then the unknown parameters are A and B. A and B are the parameters which we arrange as a vector. The vector parameter theta equal to A B transpose. So oftentimes we can see that as a column vector A and then B. And if we recall, previously we talked about a parameter which is one single parameter or a group of parameters which are, for example, this one, a group of two parameters A and B. So it could be one, or it could be two, or it could be many parameters. Okay, so let in x, uh, as the data vector, which is x0, x1, all the way to xn. Then the PDF is p of x conditional parameter equal to something like this. And then how can we write this out? This is a multivariate Gaussian. Multivariate, meaning that you have multiple Gaussian. Multiple Gaussian. Right? You have multiple Gaussian, and you multiply all the PDF together, you get 2 pi sigma square to the degree of n divided by 2, and then exponent of minus 1 over 2 sigma square summation xn minus a minus bn. How come? If we use xn to minus a and b, x minus a minus b n, then it will be equal to w, right? If it's equal to w and this is Gaussian, we can write it out. So we can write Gaussian distribution with mean 0 and then sigma square. So this whole thing goes to here. This whole thing goes to here because it's the Gaussian variable. Of course, the randomness comes from x, and this is the parameter. The choice of a straight line or a signal component is consistent with the knowledge that Dow Jones is hovering around 3,000.